Hey, welcome back to Fat Mama Physics. In this video, we're going to do example 1 from line is emission spectra 7.10? I think it's 7.10. 7.10. So hopefully you have an idea of how all of this works in terms of electron excitement, the discrete energies that are involved, the specific energies that are associated with a photon of light. So this video will only focus on going over the examples, so applying your understanding, okay? So let's start with example 1. One of the colors you observed through the hydrogen lamp is of a reddish color. So this is the wavelength given in nanometers, okay? Using the chart on the right, okay, so it's over here, determine the energy levels involved in such a drop and of course, name the series. Terrible wording here. So what we're going to do is we're going to take this wavelength. We're going to try to figure out what the energy of the photon is needed to, I guess it is, it looks like a photon is emitted. So it causes the electron to drop from a higher energy level to a lower energy level, in which the energy transition between the two levels is equivalent to the energy produced by this photon, or the energy that's associated with this photon that is released. So let's do that first. We know that this equation here, the Planck's-Einstein relation is E equals to H and this little, not a V looking thing, but it stands for the frequency. And of course, since we have the wavelength, we're going to use the speed of light instead. So the speed of light over the wavelength, since the frequency is just speed over wavelength, we can use this to find the energy associated. We need the constant H. You are not required to memorize it. It is Planck's constant, and you can find this in your data booklet, where H is 6.63 times 10 to the power of negative 34 joule seconds. Okay, and the speed of light, 3 times 10 to the power of 8 meters per second, divided by the wavelength here, 656.2 times 10 to the power of negative 9 meters. So after putting all that in, we're going to get the following. Okay, this gives us 3.031 ... times 10 to the power of negative 19 joules. But it looks like the energy transitions here uses electron volts. So to convert this into electron volts, we're going to divide by 1.6 times 10 to the power negative 19. And that's how many joules you would get per electron volt. And I get 1.8944 ... electron volts. So we're gonna go to our graph here, and hopefully we're gonna find a difference here that's gonna give us roughly about 1.89. And I know this is gonna be a little bit trial and error, so let's take a look. We have a drop here from negative 1.5 to negative 3.4. This is a drop of 1.9 electron volts. That comes pretty close to 1.89. So let's double check if there's other possibilities. I don't see any other possibilities, and keep in mind that the electron can only be in these specific energy levels. So there's no way for you to say, oh, it could be here to there, or there to there or something. That does not happen because these electrons occupy discrete energy levels that are finite in nature. So this looks like the most likely energy drop, which is going to be in the Balmer series, in which all of the electrons drop to the second excited state. So this is the change, or actually 1.89 or 1.9, and it's in the Balmer series. And you know what? I'm going to continue on with example 2 because it's not going to take too much time. Here, what frequency is needed for a photon to excite an electron from ground state to n is equal to 4? So we are kind of going in the opposite direction. We're looking at the energy level change and we're using that to figure out what the frequency of light is needed. So if we take a look at this diagram here, from the ground state, n is equal to 1 to n is equal to 4, we go from an energy state of negative 13.6 electron volts to negative 0.85. So first of all, we need to figure out this energy difference, and that's the energy of the photon needed in order to excite this electron. Here I get 12.75 electron volts, and since the Planck's constant uses joules, joules to -1, so using joules, we're going to convert electron volts into joules by multiplying this by 1.6 times 10 to the power of -19 joules per electron volt. This is going to give us 2.04 times 10 to the power of -18 joules. And this is going to be the energy associated with whatever frequency that we have here. So to figure out this frequency, we're going to need to divide both sides by the Planck's constant in order to get our final answer. So 2.04 times 10 to the power of -18 is we're going to divide that by the Planck's constant, 6.63 times 10 to the power of -34 joules. Oopsies, that should be joules, joule seconds. Joule seconds. So this is wrong over here as well. So I'm going to change that. Okay. Joule seconds. And we get a frequency of 3.0769. And for about 2 sig figs, this is going to be 3.1 times 10 to the power of 15 hertz, or seconds to the -1 for frequency. Okay, so there you go. In fact, we can just do a little see what this is in terms of wavelength for reference. And wavelength, this is in a getting close to the UV section. This is like 97. This is 97 nanometers. 98 nanometers, which is going beyond the visible spectrum for sure. Okay, so that's it. We can do a quick self-check here. When the electrons drop in energy state, so they lose energy, they give off a photon, that's going to give us our emission spectrum. On the other hand, if an electron absorbs a photon of a specific wavelength, then we are going to see missing bands on our spectrum that we analyze from a sample, and those missing bands will correspond directly to those energy levels. We call this the absorption spectrum, and all that is between these two spectra is emission gives us colorful lines. Only specific ones. The absorption spectrum is almost like the inverse of it. It's the entire spectrum, but only specific lines are missing in correspondence to the energy levels of the photons that are absorbed. Okay, so there you go. That's line spectrum for you. I think I have another full-on IB question coming up to give us more practice. So hopefully this was helpful. I wish you the best of luck. Thank you for watching. Fat Mama Physics signing out.